Hello, can you hear me?
Absolutely. Perfect. Thank you.
Okay, thanks. So first of all, I would like to thank Mr. Chairman for the introduction, and also all of the organizers for putting together this nice meeting in the difficult times when we don't have any conferences. It's really a wonderful initiative. I will present some work which we have done actually quite some time ago, but I think I never presented it at NMR conferences, so perhaps it's a good opportunity. So this work is a result of cooperation between our institute and Bunkowski Group in Darmstadt. So let me first start with acknowledgements. So from ITC, from Novosibirsk, there are several people involved. So for many years, I'm working with Alexei Kirutin and Alexandra Yurkovskaya, and also recently some younger colleagues joined in, Vitaly, Danil, and Natalia. We also enjoy cooperation with the Bunkowski lab. So people involved and were Grit Zauer, Stefan Knecht, and Gert himself. And also we really benefited from working with Professor Limbach, who is specialist in dihydrogen complexes with hydrogen, etc. That's the outline of my talk. In this talk, I would address a somewhat provocative question. Is spin order of H2 in a PHIP or SABRE solution given by singlet order or not? So you'll see that the issue is not so as simple as it seems first. So first I will introduce a kind of conundrum or riddle. That's the riddle of the partially negative line of free H2 in a PHIP or SABRE solution. PNL is partially negative line. I will provide an explanation of this effect, tell what we can learn from this effect, and also explain why it is useful for PHIP or SABRE. Okay, let me first start with the introduction of the PNL effect. If we talk about PHIP or SABRE system, in solution, we always have free H2 dissolved in the liquid and H2 bound to a complex. In the case of PHIP, this is usually a rhodium-based catalyst. In the case of SABRE, this is an iridium-based catalyst. And of course, there is always exchange going on between the two forms. If we talk about NMR properties, in this particular system, the bound form is not visible in NMR. We were not able to acquire the signal. And free H2 is expected to be just a single line because H2 is an A2 system. It should have just one NMR line. That's the naive expectation. So let me now show you what kind of spectra we can observe in real experiments. So in this case, we're actually able to track PHIP formation in real time. That's thanks to Alexei's hardware developments. So in this particular example, we start with a compound with a triple bond. We hydrogenate it, get a compound with a double bond, and then we hydrogenate it further. Finally, all bonds are saturated. In the spectrum, we can resolve all the lines of the compounds of interest. So you see here green, blue, and red lines corresponding to the compounds marked in the same color. And if you look how the signals are changing with time, first of all, we can look at the concentration of different substances. So you see that the starting compound is very quickly gone after we start bubbling. So then we produce the intermediate compound with a double bond, and it is slowly converted to the compound with the saturated bond. So you see that all these processes, except for the first reaction, are relatively slow. They take minutes. So if we look at PHIP, PHIP formation is only visible at relatively short times when we are actually bubbling. After we stop bubbling with parahydrogen, reactions are still going on, but polarization is no longer produced. So if we talk about the signal of H2, you see that it builds up because we introduce H2 in our system, and then it decays because H2 leaves the solution. But also we see some kind of strange signal marked here with these black stars. I will introduce it in a second. This is also a transient signal, which follows more or less the same trend as the PHIP signals. So it's important to note that we have hydrogen in our system for quite a while and reactions are going on, but at some point we don't have parahydrogen anymore and we don't have PHIP. So singlet order lifetime is actually limited. Okay, so now let me go to this kind of riddle that we had to solve. That's the shape of the line of free H2 dissolved in solution, and that's the PNL. So you see that we don't have just a single absorptive line. We have a kind of anti-phase line with the positive and negative components. So that's the riddle we wanted to solve. So question is, why isn't it just a single line? Why are there two components, although a two system should have just one line in NMR? So that's the conundrum. Before I explain the physics behind it, let me give some experimental facts about PNL. So, of course, PNL is only seen when you work with parahydrogen. With thermally polarized H2, you never see it. PNL can actually show up even if you don't have a substrate. It's just enough to have free form and bound form of H2 and exchange going on between them. PNL is anyway a transient effect, so it completely disappeared after singlet triplet mixing in H2 is accomplished. Somehow it's also connected to spin order of parahydrogen. You can, of H2. You can check it very easily by doing selective excitation of H2. In this case, it's still there. It's really connected to spin order of H2. So the intermediate conclusion that we got is that PNL comes from polarized H2. Of course, it's important to know that it's polarized also hydrogen. It's not related just to parahydrogen, because parahydrogen still would not have any NMR signal. So it's really spin order of also hydrogen that we produce here. So having understood that, we try to investigate this further, and we try to characterize the polarization. And the interesting facts is that if you do OPSI detection, which detects only two spin order, you see this contribution from PNL. And if you do a standard flip angle dependence of your signal, then the funny fact is that the signal is maximal for 45 or 135 degree pulses. It's 0 if you apply 90 degree pulses. Basically, you have sign of 2-phi dependence. So this is some kind of two spin order in the A2 system that we deal with. So now we have to figure out where polarization comes from and why we can observe it. Before I go into that, I would like to tell about similar observations from other groups. So in this example from Zhivanitka and co-authors, you can also see a funny shape of the signal of H2 dissolved in solution. So actually here, that's the example is dealing with metal-free PHIP with ANSA aminoboranes. So here you have a complex with H2 with hyperpolarized signals, which are highlighted in the spectra, and you also have free form of H2. So in this particular case, formation of this anti-phase line is as follows. So first you generate two spin order I1Z, I2Z in the complex, then you apply a pulse converted into anti-phase magnetization, which is then transferred to also H2, and you actually see this funny signal. So it's similar to our case, but it's not the same situation, because we actually study spin order of H2 itself, because we can check that selective excitation of H2 gives rise to this PNL signal. So it has somewhat different origin. Of course, two things are related, but they are not the same. Okay, let me now go to the explanation. So the idea here, actually, the first idea is pretty old. It dates back to works of Pagan. The idea is that when H2 binds to the complex, two protons become non-equivalent, symmetry is broken, and chemical shift difference kicks in. So then, if you look at the singlet state, which is shown by two anti-parallel arrows in this simple vector model, that's state with anti-parallel spins, and the spins are precessing around the B0 axis. If the chemical shifts are different, then the precession frequencies are different. One arrow is precessing faster than the other one, and at some point we get to a state where the arrows are no longer anti-parallel. Of course, there is no Z projection, but it's a different state. In this simple vector diagram, that's the T0 state, which means that we have singlet to T0 conversion. So after that, the complex dissociates, and we have in solution also hydrogen with the T0 state enriched. So the spin order here is actually given by the excess population of the T0 state of the triplet manifold. So this is equivalent to the two spin order I1Z, I2Z. That's part of the explanation, of course. So first of all, we obtain hyperpolarized also hydrogen. That's what we are looking at. Then by NMR pulses, we can excite two transitions which correspond to T0T plus and T0T minus. And it is relatively easy to show that excitation efficiency is maximum for 45-degree pulses and 0 for 90-degree pulses. But there is a problem. So these two coherences in the triplet manifold completely compensate each other at all times because they evolve at identical frequencies and they have opposite amplitudes. So whatever we do, these coherences cannot give rise to observable magnetization. So to get the explanation why we see this effect, the PNL, we have to keep in mind that we have exchange. So exchange gives rise to polarized also hydrogen in solution, but we have to keep in mind that it keeps going when we acquire the FID. So we start certainly with zero magnetization, as it's shown in this diagram, that the two arrows corresponding to the two coherences in the triplet state are anti-parallel and evolve at the same frequencies in free H2. However, when H2 binds to the complex, they start evolving differently. So for this reason, this cancellation effect is not complete. And even when H2 leaves the complex, we are still left with some magnetization which we can detect. And this magnetization gives us the PNL line shape. We tried to check it with calculations, that's level space calculations, where we considered spin evolution in the free and bound form and exchange. The starting spin order was given by the population difference, by the excess of population in the T0 state. And then in experiment, as the real part of the signal, you get the PNL. Imaginary part of the signal is also looking funny. It's not just a line, a single line. It also has negative components. When we do the calculation, we can actually reproduce these line shapes. So the result, also the phase, depends on the sign of the J coupling in the complex. If the coupling is negative, that the sign is different. So it seems that really everything works properly, that we reproduce the line shape, the flip angle dependence is proper, the real and imaginary signals are proper. It seems that we really understand what's going on here. In this particular case, there is also a simple explanation which was proposed by Professor Limbach. So you see that these two coherences in the triplet manifold correspond to absorptive and emissive lines. When we have exchange of H2 with the bound form, where the two protons have different chemical shifts, each of these coherences is exchanged with two single quantum coherences. So we have two absorptive transitions and two emissive transitions. So now we also have exchange going on between the free and bound form. In this particular case, that's slow exchange, where we normally consider only broadening of the signals, but we have to keep in mind that anyway, signals also move slightly to the center of the spectrum. So then this absorptive component is exchanging with two absorptive lines in the complex, and emissive component does the same. So as a result, both of these lines get a bit broader, but also they experience small shifts. And the shift is not identical for the two components. So therefore, we can conclude that PNL is a superposition of two strong lines which have opposite signs and have tiny splitting. So as a result, if we sum up two lines, we get the PNL line shape. So PNL is actually a differential effect. Okay, so if we talk about the schemes of PNL formation, the first scheme proposed by Zhevanitka and co-authors implies that you generate two spin order in the bound form, then you apply RF pulses and generate anti-phase polarization, it is transferred to the free form. In the case which we consider here, you generate T0 order in the free form, then you apply RF pulses, and during FID, you avoid this complete cancellation of the two lines due to chemical exchange, due to symmetry breaking. Okay, now let me tell what we can learn from PNL. The answer is actually pretty simple. We have to keep in mind that PNL comes from two facts. So first of all, that's chemical exchange, and second, that's symmetry breaking in the complex. So the two protons should have different chemical shifts. These two facts tell immediately what we can learn. We can actually probe chemical exchange, and we can also determine NMR properties of the complexes. So in this particular example, in the PHIP system, without PNL, the complex is not visible. We could not see it in doing numerous experiments with thermal polarization. Okay, so if we want to use the PNL effect, we need to update the experimental protocol. In this case, it's like this. First we bubble, then we apply a lone RF pulse. It's a pseudo CW pulse. And then we use the OPSI sequence to detect the PNL. So the idea is that the RF pulse can excite the transient complex with H2, and then it disturbs singlet triplet mixing. So the PNL is going to be affected by that. Actually, the intensity is simply reduced. So what this experiment tells us is the following. In this case, we stepwise varied the frequency of the lone RF pulse. And then if we look at the OPSI intensity, OPSI signal intensity as a function of the RF frequency, we see two components. The first one is actually pretty straightforward. It simply corresponds to free H2. So if you start exciting at this frequency, we simply kill the signal by saturating it. But we also have one more component, a broad one at negative chemical shifts. This corresponds to excitation of the complex. The results, the experimental results match pretty well with the simulation. In good agreement. So actually we can say that by indirect detection, the complex becomes visible. It's important to know that when we do this experiment with thermally polarized H2, then we can't see the complex. By comparing theory and experiments, we can determine properties of the complex. We can say that J coupling of the two protons in the complex is positive. We can estimate the chemical shifts, and we also give an estimate for the exchange rates. Same ideas can also be used in SABRE systems. That's just one example which I show here. I would like to briefly mention also our cooperation with Danila, Barsky, and Alex Pines. So these are CEST experiments, chemical exchange saturation transfer experiments, done with normal hydrogen, not with parahydrogen. So the idea of experiments is pretty simple. You pump at variable frequency and excite different complexes, and excitation or saturation is transferred to free H2 signal, and then you see a reduction of this signal. If you vary the radiation frequency, you can see a number of lines in this spectrum, which correspond to three complexes. One complex is very easy to identify. That's the main complex with two equatorial pyridine ligands. You also see it in the thermal spectrum. It's pretty easy, but there are also two other complexes, and it's possible to prove that in these complexes, one of the pyridines is replaced either by the counter-ion or by the solvent molecule. You can also try to use PNL. This would give additional insights. Okay, so let me now go to practical consequences for PHIP and SABRE, which we actually did use from this discussion of the spin order of H2. I would like to show you several examples. The first example is dealing with SABRE formation at high fields. Originally, SABRE experiments were done at low fields. At least polarization was done at low fields, which correspond to strong coupling of spins and efficient spontaneous polarization transfer. But also Koptyuk and Chekmenev groups have demonstrated that such experiments can be done at high field, and without any RF pulses, you can polarize your substrate. So there is some kind of mechanism for spontaneous polarization transfer, which is operative at high fields. Enhancements are actually moderate, but still the experiment is useful because it's very easy to run. So our goal was to determine the transfer mechanism, and I guess that we are able to show that transfer goes in 3 steps. So first of all, we generate the two-spin order of H2, I1Z, I2Z. So the second step is that we have a cross-correlated relaxation, which converts this two-spin order into polarization of H2. Actually, you can see it from the spectrum. The lines corresponding to free and bound H2 are much stronger than the lines in the thermal spectrum. Enhancements are of the order of 20. Third step is actually trivial. You just have NOE-driven polarization transfer. Let me explain why we think that way. I do it only for step 1 and step 2. Step 3 is too simple to be discussed, I think. So with step 1, justification is as follows. Spin order of H2 is really anti-phase order. We can conclude it from looking at the signal of free H2. We get this PNL signal. That's an indication that we have hyperpolarized ortho hydrogen. But also, if we look at the signals of bound H2, we see that there are positive and negative components of the lines, which we can simulate only if we assume that both singlet and T0 states are equally populated. If we assume singlet order, then some of the intensity ratio of different lines is not proper. So actually, this means that we start with anti-phase order. So the next step is conversion of, we start with two-spin order. The next step is that we convert two-spin order into polarization. And we believe that this happens due to cross-correlated relaxation due to two mechanisms. That's dipolar relaxation and CSA. It's actually possible to do test experiments. One of them is that we first invert polarization of H2. So then it relaxes, and while it relaxes, it is also transferred to I1Z, I2Z spin order. This we can check by applying the OPSI block. And this is really true. If we do the OPSI detection, then we see here anti-phase lines, which tells us that we have cross-correlated relaxation between these two types of spin order. And also the field dependence of polarization is really proper and consistent with this cross-correlated relaxation. Okay, everything is fine, and the NOE step is actually simple and standard. Okay, let me tell you why this conversion issue is important for practical purposes. The idea is that spin order has to be taken into account when we do polarization transfer and when we optimize our pulse sequences. In the first example, I show you the effect of ST0 conversion on inept type pulse sequences. So in this case, we start we bubble, and then we try to transfer polarization from protons to nitrogen. We first introduce an inept block. The first angle is, the first pulse is a 45-degree pulse. So then we convert anti-phase polarization to in-phase polarization. Then we do exchange and detection. So if you look at the enhancement as a function of delay times, you see that it's somewhat different for singlet order and two-spin order. And simulation with two-spin order actually matches the experimental observations better. But I would also like to show you an example which looks really much more convincing. It's not just a small refinement, it's a big effect. So in this case, we transferred polarization to nitrogen in the manner of LIGHT-SABRE, where you can apply an on-resonant pulse which generates polarization along the B1 field on the nitrogen. Then you apply a 90-degree pulse to get longitudinal polarization. Alternatively, you can apply an off-resonant pulse, which generates you some Z polarization right away. So we also did this LIGHT-SABRE experiment, but we also did it with a small modification. We applied a 90-degree pulse on the protons before the transfer. So question is, why do we do that? What can we gain, and why should it work? Actually, if we start with singlet order, it really makes no sense to apply this 90-degree pulse because it doesn't change the state of the protons. Let's look at this a little bit more closely. I introduced the same kind of spin system as Thomas Theis did. So we have two protons and two nitrogens. We have proton-proton, nitrogen-nitrogen coupling. And we also have these cross couplings. If we look at the Hamiltonian in the rotating frame, we have the main term, which contains Zeeman interactions and proton-proton and nitrogen-nitrogen couplings, and also this perturbation term with cross couplings. So it's possible to show that levels of the main Hamiltonian cross when B1 matches the sum of these two J couplings. Under these conditions, level crossing conditions, additional terms kick in and start mixing them. And then we have mixing of the kind, for instance, singlet. Singlet goes to T0, T plus, meaning that we polarize the nitrogen along the effective field. So that's actually what we want. But now an important issue is that what we start with the ST0 population difference, which we convert. And if we start with singlet order, the population difference is just equal to 1. But if we start with two-spin order, if ST0 conversion has already occurred, then population difference is 0 and the method should not work. But the good thing is that we can partly recover the population difference if we apply a 90-degree pulse. We actually recover half of the population difference. Okay, we should really gain from this additional pulse. So let me show you briefly an example of how it works. So here I compare all these excitation schemes. And for instance, you can compare off-resonant light sabre with off-resonant SLIC-SABRE, same method with a 90-degree pulse on the protons. And you see that there is a gain by a factor of more than 2. And signal enhancements then really become comparable to what you get in SABRE trees. So really do care about the 90-degree pulse and don't forget about it. I think that further experiments I can only very briefly introduce. We keep studying this conversion in different systems, also as a function of magnetic field. Really conversion on the catalyst is always an important issue, and this ST0 contribution to the overall conversion is also important. So the conversion is strongly field dependent as well as the PNL intensity, and usually there are several complexes which affect that. So we actually now trying to minimize these effects. Okay, I think I skip these slides. I go to
just
conclusions.
into the questions now, so thank you.
Oh, okay.
Konstantin, why don't you finish up? That's great.
Oh, may I quickly say that I hope that I convinced you that spin order of H2 is an important concern in this experiment. Spin order is not necessarily the singlet order, so please be a little bit careful. So I'd like to thank you all for your kind attention and show you a kind of slogan from the city of PERM, located at the bank of the Kama River. Translation is happiness is not far away. I hope that soon we are through this difficult period. Thank you.
That's great. Thank you very much for an outstanding talk. I have a few questions for you. The first is, does the enhancement of the orthohydrogen happen early on in the experiments or after the substrate is consumed? Or is it competing with the substrate and observed throughout the experiment? So what are the dynamics of the enhancement on the ortho side?
I would say that these processes are going on simultaneously. So in some cases, you don't even need a substrate. Actually, in the very first example with PHIP, we started these experiments using a substrate, but at some point we did not even do that. So if you have exchange going on, it might be that you already have some conversion before you run the actual PHIP experiment. Yep. And basically, this process is always run in parallel. Of course, how efficient is the conversion depends on many factors. How you make your sample, what is the pressure of H2, how much H2 you have, how much catalyst you have. And I think that I don't give you any universal answers here. There might be cases where it's very important to keep that in mind, and there might be cases where it's not so important.
And we have one last question, which is, have the light sabre or SLIC-SABRE experiments been simulated in spinach yet?
No, we never tried that. We usually have home-written codes, and we never compared that to, well, we never did simulations using software of other people. But of course, we are open to such studies.
That's great. With that, we should thank our speaker again.